Have you ever felt the sun's warmth on your skin on a bright summer day? It's a simple pleasure, yet it raises a profound question. What fuels this incredible star and bathes our planet in life-giving light? The answer, my friends, lies in the heart of the sun, where a cosmic dance of unimaginable power unfolds. The sun is not a giant campfire burning fuel as we know it. It's an immense sphere of plasma, a state of matter so hot that atoms are stripped of their electrons. This plasma is in constant motion, driven by a force far more powerful than any chemical reaction. This force, the secret to the sun's energy, is nuclear fusion. Imagine a journey to the center of the sun, a voyage that takes us through the vast expanse of space, closer and closer to the heart of our solar system's fiery giant. As we descend, we're met with unimaginable pressure and temperatures exceeding 15 million degrees Celsius. The environment becomes increasingly hostile, with plasma swirling and solar flares erupting around us. This is the sun's core, a place where the rules of ordinary matter bend to the immense forces at play. Here, the conditions are so extreme that they defy our everyday understanding of physics. Here, hydrogen atoms, the simplest and most abundant element in the universe, are squeezed together with incredible force. These atoms, which are the building blocks of the cosmos, are subjected to pressures millions of times greater than what we experience on Earth. Under this extreme pressure, they overcome their natural repulsion and fuse together. This process is not just a simple collision, it's a dance of particles, a symphony of atomic interactions. This fusion process, the merging of atomic nuclei, is the engine that drives our star. It's a continuous cycle of creation and destruction where new elements are forged in the crucible of the sun's core. When hydrogen atoms fuse, they form helium, a slightly heavier element. This transformation is a fundamental process that powers not only our sun but all stars in the universe. But something remarkable happens during this transformation. A tiny bit of mass is converted into an enormous amount of energy. This energy radiates outwards, providing the light and heat that sustain life on Earth. It's a reminder of the incredible power locked within the smallest particles of matter, a power that fuels the stars and illuminates the cosmos. This conversion of mass into energy is described by Albert Einstein's famous equation E equals mc squared. Energy, E, equals mass, m times the speed of light, c squared. This simple equation reveals a profound truth. Even a tiny amount of mass can release a staggering amount of energy. In the sun's core, this process happens billions of times each second. The energy released from these fusion reactions takes the form of high-energy photons, packets of light that carry the sun's energy outward. These photons begin an epic journey, a slow and arduous climb from the sun's core to its surface, a journey that will take them thousands of years to complete. Section 4. The long climb to the surface. Energy's meandering path. The sun's interior is a chaotic and dense environment, a place where extreme pressures and temperatures create a turbulent sea of plasma. The photons, carrying the energy of nuclear fusion, don't travel in a straight line. Instead, they embark on a complex journey, constantly interacting with the dense matter around them. These photons are absorbed and re-emitted by atoms in the sun's interior, a process that causes them to bounce around in a seemingly random manner. This erratic movement is known as the random walk. This journey can take a single photon tens of thousands, even hundreds of thousands of years to complete. Imagine a photon born in the sun's core. It will spend millennia zigzagging through the dense plasma before it can finally escape. The energy released in the sun's core today won't reach the surface and shine out into space for millennia to come. This delay is due to the immense density and chaotic nature of the sun's interior. As the photons travel through the sun's radiative zone, they gradually lose energy. This energy loss causes their wavelengths to stretch, shifting them into the infrared part of the spectrum. This transformation is a testament to the immense distances and timescales involved. Finally, after their long and arduous journey through the radiative zone, the photons reach the convective zone. Here, giant plumes of plasma, like massive boiling bubbles, carry them the rest of the way to the surface. This final leg of their journey is much quicker, as the convective currents rapidly transport the energy outward. Once at the surface, the energy is released as sunlight, which travels across the vast expanse of space to reach Earth. providing the light and warmth essential for life. The journey of a photon from the sun's core to its surface is a remarkable testament to the dynamic processes that power our star. Section 5. Birth of sunlight, the photosphere's glowing spectacle. At last, the photons reach their destination, the photosphere, the sun's visible surface. This journey, which began in the core of the sun, has taken thousands of years. The photons have been bouncing around, colliding with particles, and slowly making their way outward. Here, the temperature is a relatively cool 5,500 degrees Celsius, and the photons are finally free to escape into space. This temperature, while scorching by Earth standards, is much cooler compared to the sun's core, which reaches millions of degrees. This is the moment sunlight is born. The light that we see and feel on Earth starts its journey here in the photosphere. It takes just over 8 minutes for this sunlight to travel the 93 million miles to our planet. The photons, carrying the energy generated in the sun's core so long ago, stream out in all directions, bathing our solar system in their warmth. This energy is crucial for life on Earth, driving photosynthesis in plants and influencing our climate and weather patterns. The photosphere is not a smooth surface, it is a dynamic and turbulent layer constantly in motion. It's covered in granules, each the size of a continent, caused by the convection of plasma beneath. These granules are the tops of convection cells, where hot plasma rises, cools, and then sinks back down, creating a constantly shifting pattern. Sunspots, cooler and darker areas caused by magnetic activity, also dot the photosphere, reminding us of the sun's dynamic and ever-changing nature. These sunspots can be larger than Earth and are regions where the sun's magnetic field is particularly strong, inhibiting the flow of hot plasma and causing the temperature to drop slightly.